Hello everyone, welcome to another session of our online class. This is Mr. Lemes Hailu, your grade 12 calculus teacher. During this week, we'll be looking at chapter 9, section 1, which is about sequences. And the objective of our lesson is to define a sequence, to find arithmetic and geometric sequences, and to find the limit of a sequence. A sequence is a list of numbers written in an explicit order. A(n) is equal to A1, A2, A3, goes on until AN and even goes beyond. A1 is called the first term. AN is called the nth term of the sequence. Any real valued function with a domain, a subset of the positive integer, is a sequence. If the domain is finite, then the sequence is a finite sequence. In our studies, we will mostly be concerned with infinite sequences. A sequence is defined explicitly if there is a formula that allows you to find individual terms independently. Example, let's say n is equal to negative 1 to the power of n divided by n squared plus 1, where n is a positive integer. To find the hundredth term of this sequence, you simply plug in 100 in place of n, and you get 100 is equal to negative 1 to the power of 100 divided by 100 squared plus 1, which gives you 1 over 10,001. A sequence is defined recursively if there is a formula that relates an to previous terms. For example, let's say b1 is equal to 4 in a sequence bn is equal to bn minus 1 plus 2 for all n greater than or equal to 2. N starts from 2 because b1 is already given 4. We find each term of this sequence by looking at the term before it. Since b1 is equal to 4, b2 is obtained by b1 plus 2. Since b1 is 4, 4 plus 2 is equal to 6. The third term of this sequence is b3, which is b2 plus 2. b2 is 6, 6 plus 2 is equal to 8. b4, or the fourth term of the sequence, is b3 plus 2. Since b3 is 8, 8 plus 2 gives you 10. You have to keep going this way until you get the term you are looking for. Now let's move on to looking at the two different types of sequences, arithmetic and geometric sequence. We will start with an arithmetic sequence. A sequence an is an arithmetic sequence if it can be written in the form a plus d, a plus 2d, and goes on until a plus n minus 1 times d corresponding to an for some constant d. The number d is the common difference of the sequence. Each term in an arithmetic sequence can be obtained recursively from its preceding term by adding d. That means an is equal to an minus 1, which is the preceding term, plus the common difference d for all n greater than or equal to 2. Or explicitly, we can define an is equal to a1 plus d into n minus 1. Now let's see some examples to help us understand about arithmetic sequences. Given the arithmetic sequence -3, 1, 5, 9, and so on, find the common difference, the ninth term, a recursive rule for the nth term, and an explicit rule for the nth term. Okay, to find the common difference of this sequence, we can pick up any term and find the difference between that term and the preceding one. For example, if you pick up 1, the preceding term is -3, 1 minus -3 is +4. If you pick up 5, the preceding term is 1, 5 minus 1 is 4. Similarly, you can go on 9 minus 5 is 4. One thing you have to pay attention to here is that the difference we are looking for, or the common difference, should be constant throughout the terms of the sequence. The second one is to find the ninth term. To find the ninth term, we need to use our explicit formula, n is equal to a1 plus d into n minus 1. Good. Our first term is -3, so a1 can take -3. We already found the common difference d is equal to 4, so we need to plug in these two values and write a9 is equal to -3 plus 9 minus 1 times 4. That gives you 29. C. Find a recursive rule for the nth term of this sequence. A recursive rule means we have to assign a1 which is given as -3 in the sequence, and an is equal to n minus 1 plus d, but the value of d is already found. The common difference is 4, so the formula is an is equal to n minus 1 plus 4 for all n greater than or equal to 2, since a1 is already defined as -3. The last one is to find an explicit rule for the nth term of the sequence. Since the explicit rule is n is equal to a1 plus n minus 1 times d, a1 is -3 plus n minus 1 times the common difference is 4. So simplifying this one, we get the explicit formula for the given sequence as 4n minus 7. Now let us look at the second type of sequence, that is the geometric sequence. A sequence n is geometric sequence if it can be written in the form a times r, a times r squared, a times r cubed, and goes on a times r to the power of n minus 1 corresponding to an for some non-zero constant r. The number r is called the common ratio. Each term in a geometric sequence can be obtained recursively from this preceding term by multiplying by the common ratio r, or an is equal to an minus 1 times the common ratio r for all n greater than or equal to 2. Or we can explicitly define the formula for a geometric sequence as an is equal to the first term a1 times the common ratio r to the power of n minus 1, where n is a positive integer. Now let's see another example of a geometric sequence. For the geometric sequence 1, -3, 9, -27, and so on, find the common ratio, the tens term, a recursive rule for the nth term, and an explicit rule for the nth term of the sequence. The common ratio of this sequence can be obtained by finding the ratio between any two consecutive terms of the sequence. For example, if you pick up -3, the term preceding this term is 1, you divide -3 by 1, and that gives you -3. If you pick up 9, the term preceding 9 is -3, so 9 divided by -3 is -3. If you move on, you will get the common ratio, which is constant, equal to -3. The second one is to find the 10th term of the sequence. In order to calculate the 10th term, we need to use the explicit formula, n is equal to a1 times r to the power of n minus 1. We know that a1 is 1 in the sequence, and the common ratio is -3, so we need to plug in this, and in place of n, we have to plug in 10. 10 minus 1 gives us 9, so the value of a10 is equal to negative 19,683. In part C, you are asked to find a recursive rule for the nth term, or a formula. Here we have to set a1 to be 1, and an is equal to an minus 1 times the common ratio r. Since the common ratio is -3, so an is equal to -3 times an minus 1 for all n greater than or equal to 2. And the last one is to find an explicit rule or formula for the given geometric sequence. The explicit formula for the geometric sequence is given by an is equal to a1 times r to the power of n minus 1. We have everything. a1 is 1 in the sequence, r is -3, which is the common ratio. So if you plug in properly, you will get the formula for the sequence n is equal to -3 to the power of n minus 1. When we consider sequences as functions where their domain is a positive integer n, we can find their limits, and the limits of sequences satisfy all the properties of limits of functions. For example, if L and M are real numbers, and the limit of an as n approaches infinity is L, and the limit of Bn as n approaches infinity is equal to M, then the sum rule of limits of sequences states the limit of the sum of two sequences is equal to the sum of the limits, which is L plus M. The second rule is the difference rule. The limit of the difference of two sequences is equal to the difference of their limits, L minus M. The third one is the product rule. The limit of the product of two sequences an and bn is equal to the product of their limits, which is L times m. And the constant rule is the limit of a constant times a sequence an as n approaches infinity is equal to the constant itself multiplied by the limit of the sequence an. And the quotient rule also works here. The limit of an over bn, given that bn is different from 0, or the limit of bn as n approaches infinity is different from 0, is equal to L divided by m, given that m is different from 0. Sequences can be categorized as converging or diverging sequences. A sequence is said to be converging if the sequence has a limit L as n approaches to infinity. If a sequence has a fixed limit L as n goes to infinity, then we call the sequence as a converging sequence. If the sequence doesn't have a fixed limit L as n goes to infinity, then it is said to be a diverging sequence. You can determine if a sequence converges by finding the limit as n approaches infinity. Let's say, for example, if the sequence an is equal to n minus 1 over n converges. To do this one, we simply look at the limit of 2n minus 1 over n as n goes to infinity. Since n is equal n in the denominator is common for the two, you can simplify this one to limit of 2 minus 1 over n. The limit of 1 over n as n goes to infinity is 0. So this limit goes to 2. It's obvious that the limit goes to a fixed number 2, which confirms that the sequence converges, and that limit is 2. The sandwich theorem also works for limits of sequences. If a limit of an as n goes to infinity is equal to the limit of cn as n goes to infinity, and if there is an integer n for which an is less than or equal to bn less than or equal to cn for all n greater than capital N, then the limit of bn as n goes to infinity is equal to L. Since bn is sandwiched between an and cn, and the limit of both an and cn is L, it follows that the limit of bn is also equal to L. The last example of our lesson shows that the following sequence converges and find its limit. The sequence is n is equal to cosine over n. Cosine function is sandwiched between -1 and 1. If we divide each of them by n, we'll get this expression. And again, find the limit of all the three expressions. That brings you to 0 less than or equal to limit of cosine over n. Then goes to infinity is less than or equal to 0. And this implies cosine of n over n as n goes to infinity is equal to 0 by the sandwich theorem, because the limit of cosine over n is sandwiched between two zero values on the left and right side. Okay, this tells us that the limit goes to a single fixed value, which is L equal to 0. And we say that the sequence is converging and the limit goes to 0. So with this, we come to the end of our lesson. I hope you have achieved the objectives stated at the beginning of the lesson, and keep on working on more exercises. Hope I'll see you in our next class. Bye.